Right now, you're spinning on a 12,000 kilometre wide rock at over 1,600 kilometres per hour, while the entire planet hurtles through space at more than 100,000 kilometres per hour. And yet, you feel nothing. So why? And no, the answer isn't that we live on a flat Earth or on the back of a cosmic tortoise, but it is one of those questions that seems almost naive to ask until you realise how difficult it is to answer convincingly. Because we are moving constantly. Yet, unless you've taken a rather large dose of magic mushrooms, you feel nothing. But why? Well, our ancestors didn't believe the Earth was moving either. To them, the Earth felt solid, stable, central. And every day they saw the sun rise in the east, sweep across the sky, and set in the west. The conclusion seemed obvious. The sun moves and the Earth stays still. Case closed. But here's the thing. That conclusion wasn't stupid. It was intuitive. It looked that way. Now, there's a story I've always loved, often attributed to the philosopher Ludwig Wittgenstein, though probably apocryphal in nature. Apparently he was walking through the corridors of Cambridge when he turned to a friend and asked, "Why did people once believe the sun goes round the Earth?" The friend replied, "Because it looks that way." To which Wittgenstein responded, "Yes, but what would it have looked like if it looked as though the Earth were rotating?" It's a brilliant little puzzle, because visually it would look exactly the same. The experience of a moving sun from a stationary Earth is indistinguishable from the experience of a stationary sun seen from a rotating Earth. Both would cause the sun to rise and set in the same way. So, if it looks the same either way, why did we get it wrong for so long? Well, one reason is that it certainly doesn't feel like the Earth is moving. When you open your front door and step outside, you don't get hit in the face by rushing air. There's no strange sensation of spinning or flying through space. And yet, when you're in motion, you often do feel something. When you run or cycle, you feel wind resistance pushing against your skin. Stick your head out of a car window and the air rushes past your face. But what you're feeling isn't motion itself, it's the force of the air hitting you, caused by your motion relative to the atmosphere. If the air moves with you, like inside a sealed train gliding along at high speed, you feel nothing at all. No wind, no push, no resistance. You could be travelling at 200 miles an hour, and if everything around you is moving with you, you won't feel any difference than if you were standing still. So no, your body doesn't sense speed directly. In fact, Galileo was the first to recognise that if you and everything in your immediate surroundings are moving at a constant speed together, then there's no experiment you could perform to tell whether you're moving or at rest. This idea is now known as the principle of Galilean relativity. And so perhaps that's the answer. The atmosphere, along with everything on the surface of the planet, is moving at the same constant rate as the Earth rotates. There's no relative motion between us and the air, and that's why there's no rush of wind. And that's true. But what about changes in motion? What about speeding up, slowing down, or changing direction? In other words, what about acceleration? Well, Newton's second law tells us that acceleration, any change in speed or direction, requires a force, and our bodies can be sensitive to the presence and change of such forces. For example, you feel it when a plane takes off and the seat presses into your back. You feel it when a car brakes suddenly and you lurch forward. You feel it in an elevator, not while it's rising steadily, but in that brief moment when it starts or stops. That's when the normal force from the floor shifts and your body picks up on that change. Or take a roller coaster, or a car cresting a hill too fast. When your stomach drops, what you're really feeling is a brief reduction in the support force pushing you upward. Gravity hasn't changed, but the upward push from the seat or floor has reduced, and we feel that. Or when you spin on a merry-go-round, you feel as if you're being flung outward, because your body wants to continue in a straight line. You hold on to stay in the circle, and when you step off, you feel dizzy, because the fluid in your inner ear keeps moving even after you stop. So no, we don't feel constant motion, but we do feel changes in motion, accelerations caused by forces acting on our body, especially when those forces act unevenly, when one part is pushed while another lags, when things shift unexpectedly. And that brings us back to the puzzle, because if the Earth is spinning, this means we are constantly changing direction, which means, in physics terms, we are accelerating. And according to Newton's second law, acceleration requires a force. And so, should we be able to feel this force as the Earth rotates? To quantify this, let's imagine standing at the equator of the Earth. Looking down from above along the rotation axis, we would be seen to be moving in a circle with a radius equal to the Earth's radius. If the planet rotates once every 24 hours, then any point on the equator is tracing out a full circle in that time. The distance around the circle, the equatorial circumference, is then given by 2 pi r, where r is the radius of the Earth, which is about 6,400 kilometers, or 6.4 times 10 to the 6 meters. So the speed that you're moving at, relative to the rotation axis, just by standing still on the equator, is then given by v equals 2 pi r divided by t. And if we sub in the numbers, we find a speed of 465 meters per second, which is over 1,000 miles per hour. But remember, speed alone doesn't create any sensation. It's the acceleration that matters. When you're standing on the equator, you're not moving in a straight line. You're being gently turned constantly in a circle. And any continuous change in direction means that you're accelerating. And the acceleration you experience when moving in a circle is known as centripetal acceleration because it's directed towards the centre of the circle. And we can in fact calculate it using the equation a equals v squared divided by r, where v is the linear velocity and r is the radius of the circle. And as we've already seen, if you're standing at the equator, you're moving at a speed of around 465 meters per second, and the radius of the Earth is roughly 6.4 million meters. That means that the acceleration required to keep you moving in a circular path, the centripetal acceleration, can be found to be 0.034 meters per second squared. And this is the acceleration that your body continuously experiences just to stay on the rotating surface of the Earth. But here's the thing, that acceleration is not only extremely small, just 0.034 meters per second squared, it's also constant for someone located at the equator. And across the length of someone's body there's essentially no difference. And our senses aren't particularly attuned to noticing gentle, unchanging accelerations like this. The systems in our body that detect motion, like the inner ear, are much more sensitive to sudden changes, jolts, or directional shifts. And since Earth's rotation has been effectively constant for billions of years, it's likely that we've simply adapted to it over evolutionary timescales in a way that makes it effectively imperceptible. So even though you're being curved around the planet at high speed, your body feels essentially nothing. Okay, so we may not be able to directly experience this acceleration, but we do know that by Newton's second law, any acceleration must be caused by a net force according to the famous equation F equals ma. In the case of circular motion, where the acceleration is directed towards the centre of the circle, then so too must be the force. And we can sub in the expression for the centripetal acceleration to arrive at the equation for the centripetal force. Now, assuming for the moment a perfectly spherical Earth, the acceleration due to gravity near the surface of the Earth is approximately 9.81 meters per second squared, and is directed towards the centre of the Earth. And if you're standing at the equator, gravity pulls you directly towards the centre of the Earth with a force equal to F equals mg. But not all the force presses you into the ground. Part of it supplies the necessary centripetal force to keep you moving in a circle as the Earth spins. Okay, so what do you actually feel when you stand on the ground at the equator? Well, what you're feeling is the normal force, N, which is the upward push from the ground. And this is what a bathroom scale measures. It measures the normal force. And this normal force is equal to the difference between the gravitational force and the centripetal force. And if we then sub in the expressions for these two forces, we find the following expression. This is sometimes referred to as your apparent weight, corresponding to the actual contact force supporting your body. Next, if we factor out the mass, we find the following expression, and the term inside the brackets, g minus v squared over r, is referred to as the effective acceleration due to gravity. Now, at the equator where your linear speed is greatest, this correction is largest. If we sub in the numbers, we see that the acceleration due to gravity at the equator is roughly equal to 9.776 meters per second squared. And so we see that, assuming a spherically symmetric Earth, the acceleration due to gravity at the equator is about 0.034 meters per second less than at the poles of the Earth. So why do I say that? Well, because as you move towards the North Pole, say, your linear speed drops. At the North Pole, you're not tracing out a circular path. You're simply spinning, rotating in place, like a spinning top or an ice skater spinning on the spot. Your linear velocity is essentially zero, so the required centripetal acceleration is also zero, and therefore we see that the effective acceleration due to gravity is simply equal to g. The net result is that a weighing scale will read a slightly higher value at the pole compared to the equator. To see this, imagine I'm standing on a bathroom scale at the equator with a mass of 90 kilograms. What would the scale read? In this case, gravity pulls down with a force mg, and if we sub in the numbers, we find a value of 882.9 newtons. At the same time, the required centripetal force to keep moving me in a circle is calculated by multiplying my mass by the centripetal acceleration, and if I plug in the numbers, I find a value of 3.06 newtons. And so my apparent weight would be given by the difference between these two forces, which is equal to 879.8 newtons. And so this is what the bathroom scale would register. In contrast, at the poles, the centripetal correction disappears entirely, so the scale would read the full gravitational force of 882.9 newtons. But as is often the case, there's an extra twist, because in reality, the Earth isn't a perfect sphere. It's slightly oblate, bulging at the equator due to its rotation. This means that the radius of the Earth is slightly smaller at the poles, and that makes gravity stronger there. As a result, the actual acceleration due to gravity at the poles isn't 9.81 meters per second squared, it's actually closer to 9.83 meters per second squared. So not only does the centripetal correction vanish at the poles, but gravity itself gets a slight boost. That means your true weight at the pole is slightly higher than it is on a perfectly spherical Earth, and your apparent weight at the equator is slightly lower than in our simplified example. Now, granted, these differences are small and we don't feel them directly, but they're absolutely real and measurable. Gravimeters and precision scales can detect them with ease. Even though our bodies haven't evolved to register such subtle changes, the reading on a scale genuinely increases as you travel from the equator to the pole, and that difference isn't just a curiosity, it's a direct, measurable consequence of Earth's rotation. But let's now stretch the thought experiment. Suppose the Earth started spinning faster. What would happen to the scale reading at the equator? To answer that, let's look back at our equations. We see from the centripetal force equation that as the rotation speed increases, the required centripetal force increases. It grows with the square of the velocity. On the other hand, we see from the gravity equation that as the rotation speed increases, the gravitational force stays the same, because it doesn't depend on the velocity, the speed. If we then recall our normal force equation, which tells us what the scale would read, we see that as the linear velocity of the Earth's surface increases, less and less of gravity's pull is left over to press you into the scale, and therefore your apparent weight would drop as the rotation speed increased. Now, we can visualize this. By looking at the graph, we see that as the rotation speed increases, the apparent weight, which is equal to the difference between the gravitational force and the required centripetal force, reduces down to 0. So we see that there is a point where the difference between the gravitational force and the required centripetal force would reach 0. At this point, the required centripetal force is exactly equal to the gravitational force, with nothing left over to press into the scale, and so the reading would drop to 0. And we can actually calculate the rotation speed when this would occur. We see that when the normal force is 0, mg equals mv squared over r, and if we rearrange this, we find that v is equal to the square root of g times r, and this represents the threshold speed. If we then plug in the numbers, we find a value of 7,920 meters per second. That's nearly 8 kilometers per second, or about 28,000 kilometers per hour. At that rotation speed, the length of a day would shrink dramatically. In fact, we can calculate it because we know that the time period will simply be equal to the distance travelled in one rotation, which is 2 pi r, divided by the speed. And if we plug in the numbers, we find an answer of 5,077 seconds, which equates to about 1 hour 24 minutes. Now, if we increased the speed beyond this, the inward pull required to keep you grounded would exceed what gravity can provide. There'll be no force left to hold you down, and you'd lose contact with the surface of the Earth. You wouldn't shoot off into space like a rocket. There's no engine pushing you. Instead, you'd simply lose contact, quietly. You'd enter freefall. And the crazy thing is, because you and the atmosphere are both spinning with the Earth, you wouldn't feel wind or motion. You'd feel like you were hovering weightless above the ground, remaining directly above the same point on the equator, moving in perfect sync with the surface below. This is what a surface-level synchronous orbit would look like. You'd be orbiting the Earth, but hovering right at ground level, fixed about a single point, just like a geostationary satellite, except hugging the planet's surface. But all of this depends on where you are on the planet. Everything we've discussed so far, the linear speed, the apparent weight, the possibility of lifting off, has assumed that we're standing at the equator, where Earth's surface is moving fastest. But what if we weren't? Suppose you're standing at the North or South Pole. You're still rotating with the Earth, but you're not being swept around in a wide circle. Instead, you're simply spinning in place, like a ballerina turning on the spot. The radius of your circular path is effectively 0, and so your linear speed is 0. And that means no centripetal acceleration, no need for a centripetal force, and no reduction in your apparent weight. A scale at the pole would register your full weight with no adjustment. As you start walking from the pole towards the equator, the story changes. Your circular path gets wider, your linear speed increases, and the required centripetal acceleration grows, and that subtle reduction in your apparent weight, caused by Earth's spin, gradually becomes more and more pronounced. At the equator, the effect is maximised. At the poles, it vanishes entirely. So while Earth's rotation does have a measurable effect on your apparent weight, it depends entirely on your latitude, and is strongest where the world is spinning fastest beneath your feet. And so we see that under the extreme hypothetical condition of a much more rapidly spinning Earth, the difference in what you'd feel between the pole and the equator could be very dramatic. But at the Earth's actual rotation speed, the effect, though real and measurable, is imperceptible to us. But Earth's spin isn't the only motion we're caught up in. We're also hurtling around the sun. So how fast are we actually moving through space relative to the sun? Well, the distance between the Earth and the sun is about 1.5 times 10 to the 11 metres. That's 150 million kilometres. And the time taken to complete one orbit is 1 year, which is 3.16 times 10 to the 7 seconds. Then, assuming a roughly circular orbit, we can estimate the Earth's orbital speed using the equation v equals 2 pi r divided by t. And if we sub in the numbers, we find a speed of 29,800 meters per second. That's nearly 30 kilometers per second. about 100,000 kilometers per hour. So we're not just spinning on the Earth's surface, we're also being flung around the sun at an extraordinary speed. And as we've already seen, once we know the orbital speed, we can calculate the centripetal acceleration using the equation a equals v squared over r. And if we sub in the numbers, we find a centripetal acceleration of 0.0059 meters per second squared, which is even smaller than the acceleration due to the Earth's rotation, and just 0.06% of the acceleration due to gravity at the Earth's surface. It's tiny and imperceptible. Now, just like with Earth's spin, this orbital motion requires a constant inward pull, a centripetal force, to keep us moving in a circle rather than flying off in a straight line. That force comes from the sun's gravitational attraction. And yes, we can calculate the size of that force acting on a human, and it's minuscule. But here's the key point. The acceleration acting on you due to the sun's pull is almost exactly the same as the acceleration acting on the Earth itself, and on everything around you. There are tiny differences known as tidal forces because gravity weakens with distance. The side of Earth facing the sun feels a slightly stronger pull than the far side. These differences are real and measurable. They affect tides and the dynamics of orbiting bodies. But across the scale of your own body, they're vanishingly small, completely imperceptible. For all practical purposes, you, the ground, the oceans, and the air are all falling together at the same rate. And this is where Einstein took things further. According to Einstein's equivalence principle, being in freefall is locally indistinguishable from being at rest in the absence of gravity. And that's exactly what orbital motion is, a shared, continuous freefall. If everything around you is falling at the same rate, there's no stretching, no compression, no internal force to feel. That's the key. You're not accelerating alone. The ground, the oceans, the sky, all of it is falling with you. And so you feel nothing. No pull, no pressure, no resistance. Earth's orbit is free fall on a cosmic scale. A fall that never lands. A curve that never ends. So yes, the Earth spins and it flies through space. And we don't feel it. But the evidence surrounds us. And with the right tools, we can measure what our senses miss. We see it in the slow precession of a Foucault pendulum, in the spiral arms of hurricanes. We see it in the slow rotation of the stars overhead. We see it in the Earth's equatorial bulge, in the rising and setting of the sun, in the subtle shift in weight between pole and equator. We may not feel the motion, but our instruments do. They reveal the silent truth. The Earth moves. Galileo was forced to deny it during the Inquisition, condemned by the Catholic Church for defending the idea that the Earth moves. But as legend has it, as he turned away from the tribunal, he whispered defiantly, "Eppur se muove," and yet it moves. Galileo knew the truth, and today, the evidence leaves no doubt. Thank you for listening, and until next time, goodbye. I just wanted to say thanks to all my patrons, and a special shout out to unified theorist Felix and grand unified theorist Bert Humberg. Really appreciate your support. Thank you.